Okay, so the question is, how many valid unordered hands with 4 suits? Okay. Right. Yeah. I'm going to go through 3 different ways, and 3 different ways of arriving at the same answer. But my hope is that you will get these main points whenever you encounter these counting problems. I want you to follow these steps, and I'll give more detailed explanation later. Like 1, don't jump into the math. Most students just jump directly into the math without clearly outlining their what I call construction algorithm. I'll give an example later. And then 2nd, you have to check for undercount. With your algorithm, are you able to produce all the valid hands? And then finally, the trickiest case usually is check for overcount. For each valid hand, are you able to produce it consistently, produce it through different algorithm runs? If so, you're overcounting. And if you're overcounting consistently by the same factor, you can just divide. Okay, this might not mean that much, so let's go through the examples. So let's go through way 1. And I think this is the way that you said was mentioned in your class Discord, which is first choose duplicate suit. First choose duplicate suit, then pick numbers. So following the steps, then I would first say my construction algorithm, which is saying, how do I construct a hen? So what would be a reasonable algorithm first step here? I guess we can choose the suit to double first, right? Okay, so I'll say pick the double suit, the double or duplicate suit. And then, well, we have to assign some numbers. So maybe for the double suit, choose 2 numbers. And then what is the final step, you think? To construct a full 5-card hand.
The remaining 3 suit cards.
Right. For each of the single suits, the 3 single suits, pick 1 number. Okay. That's right. So let's go through an example. Why don't you pick the double suit?
Spades.
I'll just abbreviate to say S equals spades. And then for the double suits, choose 2 numbers.
2 and 5.
Okay, 2S, 5S. And for each of the 3 single suits, pick 1 number.
6, 7, 8.
Okay. And let's say diamond, hearts, and clubs. Okay. And tada! You have constructed a hand, an unordered hand that looks like this. Right? Okay. So now we are going to test if. I should have discussed count the number of possible different algorithm runs. So let's count. How many possible different algorithm runs are there? So how many ways are there to pick the double suit?
4.
Okay. 4. And then for this double suit, choose 2 numbers.
Choose 2 numbers is it's 13 times 12.
Be careful. We want to choose 2 numbers, not necessarily order. 13 times 12 means.
2 13 times 12 divided by 2.
Yes. Or 13 choose 2. Right?
Yeah.
Yeah. Maybe I should have started with a simpler example. Okay, given 13 numbers, how many ways are there to choose? Well, 2 elements. 13 choose 2. You don't say 13 times 12 because you are overcounting
Yeah.
by 2.
That's 13 permutate 2.
Right. And even with that simple example, I could have. Okay. Well, never mind. We'll just stick to this more complex example for now. Now, for each of the 3 single suits, pick one number. How many? So I guess
39?
Huh?
Wait. 39 times 26 times
Oh,
13 divided by 3 factorial.
okay. You have to be careful. So why don't we try? So, um, as much as possible, try to think of a solution that does not introduce any overcount. So your strategy right now that you just proposed is introduce an overcount and then correct it by dividing, right?
Yeah.
Right. But we don't have to do that. If you can do it correct in the first try, why don't we do it? Well, for hearts, we have to pick one number. Well, so like in our example, after we have picked spades, that means we have diamond, hearts, and clubs left. And we say for each one, we are able to pick a number independently for each suit, right?
Let me try. Is it so the first of the 3 single suits would be 39 choose 1, then
Hmm.
26 choose 1.
Well, so when you say 39, that means you're considering all the 3 suits together. But right now I'm telling you that the single suits, by the time we reach this algorithm step, you already know their identities. You don't
Oh,
diamonds, hearts, and clubs, right? Because you have already picked a double suit. That means you already know the identity of the 3 single suits,
okay. It's 13 times 13 times 13.
right? Right. So notice that even even to reach this step correctly, there was some confusion, and that's why it's important to go through many examples and for the same problem solve it in many different ways until we're sure. Okay, but yeah, we have just counted the different ways of running this construction algorithm, and now according to our steps, first we have to check for undercount. So the question is, with this algorithm, are you able to produce all valid hands?
I think so.
Yeah. Yeah, and usually checking for undercount is easy. You can kind of intuitively see, and then you're like, yeah, this algorithm will capture. Um, um, yeah, usually you don't have to prove this. Yeah, the alg will be able to produce all valid hands. Now this is the harder one. Check for overcount, and I'll get you through this. Usually how I check for overcount is I would consider uh, an, an explicit example, a valid hand, then prove that there is only one way to run the algorithm to produce it. So let's go through the example that we just did. Okay. We have 2 spades, 5 spades, 6 diamonds, 7 hearts, 8 clubs. Now, if I were to run this algorithm, now the question for checking for overcount is, how many ways are there? Is there more than one way to run the alg below to produce this hand. So let me get you through this. For the first step, pick the double suit. You have to choose spades. Right? Have to choose spades. For the double suits, choose two numbers. You have to pick 2 and 5. And then for each of the single suits, pick one number. For diamond, have to pick 6, and so on. So the answer is no. For each algorithm run, so each algorithm run corresponds exactly to one valid hand. So the count is exact.
Okay.
Now this is the happy case, right? When we get the answer right on the first try. So the final answer in this case is 4 times 13 choose 2 times 13 to the cube. And if you run this, you will get 6, 8, 5, 4, 6, 4. Okay. All right. Now we will let's see. Wait to okay. All right. This would be the happy case if you manage to produce something without any overcount. But I should write this down. If you can produce exact count. Okay, sorry. If your approach doesn't produce any overcount, pick that. For example, just now, you instead of 13 choose 2, you could have said 13 times 12 and then divided by 2 to account for the overcount. Yeah, if you do the overcount correction way, and you can't think of a way of just like doing it right the first try, it would be trickier to get right. So, yeah. But honestly, for me, I usually it's not always easy to find like way one. It's kind of tricky, right? Your algorithm is first pick the double suit. Like that's kind of tricky.
Yeah.
But okay, assume that we are not so lucky and we have instead come up with a different construction algorithm. There are 2 more. One of them is the one that you picked in your homework actually, and that's for way 3. But let's do way 2 first. How should I call this? Okay. Take 4 different numbers for each suit, then pick last random card. Okay. Now the algorithm is like this. Why don't we try to come up with the algorithm together? What would be the first step?
Well, pick 4 different numbers for each suit. So it's 13 times 13 times 13.
Okay, sounds good. So, 4 different numbers. No, sorry. 4 numbers for each suit. Yeah, fine. We'll just do the counting immediately. 13 to the 4. And then what's the final step to construct our hand?
You only have 12 cards to choose from.
Why do we only have 12 cards to choose from?
Wait, actually, no, we have 48.
Right. So I would say pick a random remaining card. 48.
Yeah.
Right. Aha. Okay. All right. 13 to the 4 times 48. We're done.
No.
Why not?
We have to divide by.
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 All right. Well, let's do it step by step. Okay. Okay. What are the things that we have to check after we have explicitly described our construction process?
Over and under count.
Okay. Let's start with the easy one first. Check under count. Can you form, for any valid hand, can you form it with this algorithm?
Yeah.
Yep. Nope. All valid hands formable. Now check overcount. Oh shoot. Now, how do we check for overcount again?
We try to get a hand and see if we can form it.
Yep. Exactly. So let's and see how many ways are there to produce it. With this option. Okay, so let's do this. 2 spades, 5 spades. We're using the same example. So here is run 1. Can you give me an example run that will produce this? That will produce this hand using this algorithm? Pick 4 numbers for each suit, right?
Yeah, 4 numbers for each suit.
EHC.
2, 3, 4, 5.
6, 7, 8. Oh, sorry.
Oh.
For this example hand,
Okay.
you have no choice but like for the pick 4 numbers for each suit. For the diamonds and heart and clubs, it's already fixed, right?
Yeah.
What about the spades?
Guess we could do 2.
Okay. And then for the second step of the algorithm, pick a random remaining card. You would have to pick
5.
Okay. Is this the only way to run the algorithm to produce this hand?
Nah.
What's the other way?
2, 5, 6, 7, 8, and then 2.
Oh, 5, 6, 7, 8, and 2. Right? And then you observe actually after this example. So usually I start with this with the example, then I observe like this overcount factor is always 2. And this is important to notice for all hands. Do you intuitively understand why is it always 2? Why are
Well, we can swap the duplicate cards with duplicate suits.
Exactly. All right. So to come up with the valid solution, the number of valid hands is equal to the number of algorithm runs. Is this the same? Are these two the same thing?
Wait, number of valid hands is equal to number of algorithm runs.
Valid algorithm runs. Well, no, because yeah, I'm sorry. I just introduced the terms without explaining them. But if I introduce the math notation, you would understand. We have discussed that 2 times the number of valid hands is equal to the number of valid algorithm runs.
Oh yeah.
Another way of saying it is like for each valid hand that we just spoke of, there are 2 ways of producing it with that algorithm. Okay. So number of valid hands equals to number of valid algo runs divided by 2. And what's the number of valid algo runs? We have counted it before. It's these. Right? 13 to the 4 times 48 divided by 2. And again, if you plug this in your calculator, you would get the same answer.
Okay.
Right? Now, last way. Actually, no, two more ways. But these are related because I'm trying to fix your solution. Let's see. There's an alternate strategy which you kind of follow with your approach, which is count ordered hands first, then dedupe. Okay, I want you then divide by 5 factorial.
Yeah.
Right. And this is fine. Sometimes I go by this mindset too because it's easier for me to reason about ordered hands sometimes. So yeah, we can go with the strategy, but the problem now is the number of valid ordered hands. that satisfy the constraint. Okay, let's try to solve this problem. And we ignore the 5 factorial. We save it for later because that's the easy part.
Okay.
Okay. So now, way 3. Let's see. Pick. Okay. Different suit cards in order. Then pick last random card.
Yeah.
So it's like pick. For example, the example would be it's like pick something spades, then pick something diamond, then pick something hearts, and pick something clubs, and then pick random card. Well, actually, sorry. No, I should say this. Okay. No. I'll just write down everything that I have in my notes. Okay. Let's say the algorithm is pick first card, pick second card with a different suit. Okay. And then we repeat. Pick third card with a different suit, pick fourth card with a different suit from the previous ones. Okay. Then pick random card. Okay. So my advice to you is don't immediately count. Before counting, you have to make sure that the algorithm makes sense and is not an undercount. So I'll give you an example. So why don't you pick a first card? Any card.
2 ace.
Okay.
Oh, 2 spades.
No, spades and then
3 clubs.
Okay.
4 hearts. 5 diamonds.
And then pick a
3 spade.
Okay. Now, my question. Now, what is the first check that we have to do?
The undercount.
Right. Now, what do you think? Remember, now we are talking about ordered hands. Is this an undercount?
No.
Well, let me ask you this. Actually, no. If I ask them, okay, let me. Okay, it is an undercount, but I want you to. Okay, fine. I'll just tell you. It is an undercount. Can you think of why? That means there's a hand that this algorithm. That means there's a valid ordered hand that this algorithm fails to.
Oh, so order matters?
Yes.
Oh, okay.
But yeah, ordered hands.
Okay.
Ordered hands. Sorry. Yeah, I should clarify. But you're right. It doesn't matter. This is good enough.
Yeah, it is an undercount because the first and second card have to be different suits.
Right. First, second card will be too strong, right? You will fail to produce the card 2 spades, 3 spades in a row. Right? So let's take this spades and this not one of them. Okay, and now we are going to talk about the last way, which is closest to the approach that you wanted to do. Let's correct this. Okay, let's correct way 3. Let's see. So the problem is we need to be able to decide where to insert the final random card, right? So let's say we have already picked 4 cards, each of different suits, right? Why don't the algorithm decide where to put the final random card, C star, into one of these blank spots?
Oh, yeah.
Okay. Now with this algorithm, it would not be an undercount because any card, any hand that you can give me, it needs to have the 4 different suits. And then the duplicate suit can be anywhere in one of these 5 spots. Okay. But let's write down the algorithm completely. And this is the final. So okay. So I copy paste the first card, second card, third card with different suits. And then for the 5th card, pick a spot to place the 5th card.
Yeah.
Wait. Let's do some counting then. Pick first card. How many ways are there? We're not talking about suits. Pick one card to place in the first spot.
52.
Okay. Pick second card with a different suit.
39.
Okay.
26.
So this looks close to your approach, right?
Yeah.
Right. See, but it's very tricky to get right. Like we have to discuss this scheme. So that's why. But we can eventually correct your approach.
Yeah.
That's from remaining.
48.
Okay. Pick a spot to place the random card. How many?
5.
There? 5. Okay. Yeah, let's go through an example of a valid hand. Okay, let's now see this hand that we were not able to produce before because the spades are together. Okay. Let's pick the first card.
3 spade.
Yeah, there you go. We already discovered that there might be something going on. Actually, wait. We'll just jump straight to the undercount overcount because going through the example, you will see the problem. Okay, is this an undercount? Can you produce any valid hand with this algorithm?
No. Wait.
Valid ordered hand.
I think I cannot, but I'm not sure.
But you don't know how to prove it, right?
Yeah.
I'll give a sample proof. Here's how. Given a hand, given a valid hand, then you must have 4 suits, right? At least 4 suits. Okay. I just read the numbers from left to right. And then I ignore a number for a suit that I already have a number for. Yeah, then given this information, you know how to produce that hand with this algorithm. First card, second, third, fourth, you just use the numbers that you just read. And for the random card and the placement, it has to be in one of those 5 spots. Okay, I explained there poorly. All right, never mind. Well, for your homework and your exam, like nobody is going to ask you to prove undercount overcount, but I promise you that I do it mentally, and that's how I'm sure that my answer is right or wrong.
Okay.
And they don't really teach this in class, which is why it bothers me. Students just jump into math and they just multiply numbers that seem right. But no, the reason why it's right is because you prove, or at least intuitively, that it's not undercounting or overcounting. Okay, but undercount, the intuition, yes, with this algorithm, you can produce any valid order of hand. What about over? So how do you prove, how do we decide if there's an overcount? We pick an example, right? Pick an example. Then we ask ourselves.
If it's ordered, then is there any way to overcount an order?
Okay, I will remind you what the overcount means. Can we produce this hand with different algorithm runs?
We can't because the hand is because the order matters. Does the order still matter here?
Yes. Pick an example. So in this example for this order 10, okay, then I have to say that this algorithm is algo for producing an order 10.
Oh, it's an overcount.
First spot and second cut for second spot and so on. I should have clarified.
Yeah, it's an overcount. Yes.
Okay. Why?
Because you can pick 3 spades for heads. I mean for hearts, 5 diamonds, and 3 clubs, and you can put the 2 spades at the front. Or you could also start with 2 spades, then 4 hearts and stuff and the other stuff. And you can also put the 3 spades later.
Yes, exactly. So I'll write down. So in the first 4 steps, as you say, you could have done this first, right?
Mm-hmm.
And then you insert 3s. Or you could also have what? Choose this first, and then you insert 2s in front. Okay. And I won't prove this again, but if you go with this intuition, you will find that for any valid hand, you are overcounting by a factor of 2. Another way of saying it is, for each valid hand, there are 2 different algorithm runs. There's always 2 exactly different algorithm runs that produce the same hand. So my question to you is, what is our final answer? Final answer for the original problem or unordered valid hands. What do you think?
Yes, you divide by 2 and then divide by
factorial. Divide by?
Divide by 2 and then divide by 5 factorial.
Yep. 6 times 13 times 48, and then divided by 2, divided by 5 factorial.
Yeah.
Was that the original answer that you got? Wait, no, times 5. Do you remember why we times 5?
Times 5 is it's like the order thing.
Yeah, pick a spot to insert the random card.
Yeah. Okay. That wasn't the answer I got.
And then you will find that it's the same thing.
Okay.
Okay. So recap. Whenever you have to count the number of like say valid hands, don't jump into math. Start by outlining your construction algorithm.
There was a glitch.
Oops.
Try again in a few seconds.
Yeah. And I would count last actually. Then you have to check for undercount and you check for overcount. How do you check for overcount? Do you remember?
Well, if you can run the algorithm in 2 different ways and get the same result.
Yes. Get the same valid hand. After you make sure that there's no undercount and overcount, or if there's overcount and you know the overcount factor, then you multiply out all everything together and divide by the overcount factor. And you might be making your way for this problem is kind of tricky to get right.
Yeah.
Like really tricky to get right. I would have picked way 1 or way 2. I suspect that many students will pick way 2 and forget to divide by 2. Yeah, but way 1 is the easiest. But even though way 1 is the easiest, it doesn't teach you on how to handle overcounts. Because for some problems, it's really hard to get like the right solution immediately. Yeah. Okay. That's all I have. Any questions? Not all.
Not right now. But I thank you very much. I new way to check my answer.
Okay, sure thing. Right.